Okay, so again, from the very beginning, what have we done? We've done, there exists non-computable functions, f bar. There, we've defined a formal proof system and what a formal derivation is. And now we've seen that, in this comment, that if there is a formal derivation for a particular statement, capital S in pi, then we have a program, P together with P prime, which will recognize a formal will find and recognize a formal derivation for S prime in finite time, constructively. I now want to go back to Godel. All right. I want to prove, I make a claim here which is a little bit more precise. It's a little bit more precise than the way I started the lecture to begin with about what Gödel's first incompleteness theorem says. But it still is going to use a couple of words and phrases that we haven't yet defined. But let me write it down here so you have some sense of where we're going. In any rich enough, and that's one of the things that I'm going to have to define, formal proof system pi that proves only true statements and I'm going to have to define what I mean by true. Proves only true statements. There is some true statement. Oh, I'm sorry, I did what I told you I don't want to do. I use this word prove. Derives. It's good that I made this mistake because it'll derive home the fact, or the point I'm trying to make, that I don't want to use the word proof because it's too confusing. I want to use derive because it's got that mechanistic sense to it. Okay, in any rich enough formal proof system pi that derives only true statements, there is some true statement that cannot be derived in pi. Okay? So that is a claim, and that's a more precise statement of Gödel's first incompleteness theorem, but I have to tell you what rich enough means, and I have to tell you what true means. Okay? And this can be done in a more general way than what I'm going to do. I'm going to do it in the context of these functions Q, the functions in Q that we started talking about. Now, Gödel's original proof had a different domain. But in terms of the moral that comes out of all of this, any rich enough formal proof system that only proves true statements, there is some true statement that cannot be proved or derived. I'm sorry, I'm using that word proof again. So now I have to tell you what it means for a formal proof system to be rich enough. What is that? Well, we're going to start by defining a statement is an F bar statement if it says for some specific positive integer x that f bar x equals 1, or it says for some specific x f bar x equals 0. So these are statements. I'm going to put them in quotes to emphasize the fact that they're statements. And when we actually look at a particular statement, the value of x has got to be specified. So for example, this might say, as an example, for x equals 15, f bar x equals 1. Okay? So this is a particular f bar statement. And I'm putting it in quotes to say that that's a statement, it is a claim that is being made about f bar 15 in this example. That the value of f bar 15 is 1. But in fact, the value of f bar 15 might not be 1. Okay? I can make statements about f bar that are not true. But f bar, remember, is a well-defined function. F bar 15 has a well-defined value, which is either 0 or 1. And you get what that value is by going back to table T. Table T relied on a particular ordering, it's possible to have, of all the computable functions in Q, that is, all the functions in A. And you look at row 15 and you look at column 15 and you find out what the value there is, and then you take the opposite. That is what f bar of 15 is. There's no ambiguity about what f bar of 15 is. So therefore, the statement that says f bar of 15 is equal to 1, that's a statement which is either true or it's false. Again, no great philosophical agonizing of what the word true means in this case. So we can make statements that I'm calling f bar statements, and each f bar statement is in fact either true or false. So any f bar statement is true or it is false. So what is a formal proof system? Is rich enough if it can state or express any f bar statement. Now here I'm saying state or express. I'm not saying derive. That's going to be the heart of what we're going to focus on. We're not saying that formal proof system pi can derive any f bar statement. We're just saying, can it write it out? Is the alphabet rich enough at the set of words you use in that proof system such that you can actually express that statement, any f bar statement? Okay. So for example, if I have a formal proof system that can make any claims about integers, that would be rich enough, because an f bar statement is a statement about integers. The input to function f bar are the integers, and the output is a 0 or 1, and those are integers. So if I have a proof system, a formal proof system, which is rich enough, which is expressive enough, that allows me to state, make a statement, any possible statement about integers, whether that statement is true or false, doesn't matter, but if I can just state it in that formal proof system, then that system is rich enough. Okay. So we're talking about formal proof systems which are rich enough, and we've also said here what it means to be true for an f bar statement to be true or false. All right. So getting to the heart of Godel. So I want to really prove Godel's first incompleteness theorem. Okay, which is in any rich enough formal proof system pi that derives only true F-bar statements there are true F-bar statements that can't be derived in pi. So this is a rewriting of what I had written earlier for Gödel's first incompleteness theorem, because I've now stated it just in terms of F-bar statements. There are some true statements that are statable in pi, but not derivable in pi. But I am now going to give you the proof, and I claim, I've been saying over and over again, that this proof is just going to be the amalgamation of all the little pieces that we've done so far. All right, so what is the proof of this version of Gödel's first incompleteness theorem? Well, suppose there is a rich enough formal proof system pi in which only true F-bar statements can be derived. And we know what it means for a F-bar statement to be true. And rich enough means that this formal proof system can actually state, write out, any F-bar statement. And we're saying that in this formal proof system, it can only derive true F-bar statements. Actually, it can derive all kinds of other things too, but I'm just saying the F-bar statements that it can derive can only be the true F-bar statements. Okay? And for contradiction to what we're trying to prove, suppose that any true F-bar statement can be derived in pi. So we're supposing that there's a rich enough formal proof system pi such that it can only, the F-bar statements that it can derive are only the true ones. It can't ever derive a false F-bar statement. And we're supposing that any true F-bar statement can actually be derived in pi. And we're trying to show that these two things cannot happen simultaneously. And the kicker, the proof of this, is that if these two things were true, if these two statements are true that I've just written out here, we could actually build a computer program that would determine in finite time the value of F bar x for any positive integer x, which would mean that F bar would be a computable function. It would be an A. But we've already proven that F bar is not an A. F bar is not computable. All right? So how do we use these two suppositions and all the things we've talked about previously to show that there would exist a computer program which can be fed any value of x and determine in finite time the value of F bar of x? Okay? How can a computer program So we're arguing that if those two suppositions were true, then f bar would be a computable function. So how would f bar x be computed by a computer program in finite time if the two suppositions were true? And then for any x. Okay? What is that computer program that would do it? All right? Well, it's p together with p prime. P together with p prime. So you start out with the statement. S bar is some statement. F bar, let's say x is 15. X bar 15 is equal to 1. Okay, that's an F bar statement. Now, it's either true or false. Okay, so program P is going to start generating strings that are statable in the proof system pi. And program P prime is going to check whether or not that each statement is in fact a formal derivation of this statement S. We said that we're supposing that the proof system pi can actually derive all the true F bar statements. And we're supposing that it never derives, pi can never derive a false F bar statement. So let's suppose that it is true. Suppose that F bar 15 is 1. So P will eventually, but in finite time, generate a formal derivation that F bar 15 is equal to 1. And P prime, evaluating, looking at each one of the successive statements that are being generated by P, each one of the successive strings that are being generated by P, will be able to recognize that string that is the derivation of the statement that F bar 15 is equal to 1. So if it happens that F bar 15 is equal to 1, then we will mechanically and in finite time recognize that, and the program P plus P prime will spit out that F bar 15 is equal to 1. Okay? Great. But what if is equal to 0? Okay? The P might actually generate the derivation, a string which is the formal derivation of the statement that F bar 15 is equal to 0, but the program P prime won't recognize it because it is looking for derivations. It is trying to look for derivations that F bar 15 is equal to 1. So how do I cure this? Well, we've actually said you can write a program P that can check any statement whether little s is a derivation of capital S. So here, the first one we're talking about, P, is checking for equal to 1 statements, F bar statements where you have equal to 1. But we can write another program that is checking for F bar statements that say that F bar of some particular value is equal to 0. So let's call that a program P double prime. So given x, the value of x, I've been saying 15, program P is generating these strings, and since f bar of 15 is either 0 or 1, eventually, and we've supposed that every true f bar statement is derivable in pi, and we've supposed that no false f bar statement is ever derived in pi, then P will generate a string. P prime will look at it and see if that string is a derivation of the f bar statement that says f bar 15 is equal to 1. If it does find that, then we know from our various two suppositions that that must be, in fact, the correct value for f bar of 15. But on the other hand, if P prime looking at that particular string that P generates does not verify that it is a derivation of f bar 15 equal to 1, then P double prime comes in and sees whether that string is a formal derivation of the statement that says f bar 15 is equal to 0. Okay? Most of the time, both of those will fail. They will say this string that has been generated, neither derives the claim or the statement that f bar 15 is equal to 1 or that f bar 15 is equal to 0. But eventually, one of those two statements P will eventually generate a string S, which is a derivation of the true f bar statement, which therefore reveals the value of f bar 15. So the first time that P together with P prime together with P double prime finds a string, which is a formal derivation of a claim about the value of f bar 15, then the program does know correctly what the value of f bar 15 is. Okay. And it's all done in finite time for any particular value of x. Now, you can figure out for yourself how to combine P prime and P double prime into a single program. I broke them up into two just for the exposition. We're not trying to be super efficient here. We just want to say that these things can be done in finite time. But what have I done? From the suppositions that we made about pi, the supposition that, first of all, it's rich enough so we can state any f bar statement, that it only derives true f bar statements, and it derives all the true f bar statements. From those three suppositions, we've described a computer program which for any x can determine in finite time the value of f bar x. So we have created a computer program that can take in any positive integer x and in finite time determine f bar x. So that means that f bar x is computable. Or f bar is computable. But we proved earlier, the first thing we proved is that f bar is not a computable function. Okay, we proved earlier that F bar is contained in Q, but F bar is not contained in A. So we have the contradiction. So the two suppositions can't both hold. And that is the proof. That is a proof of, and a completely rigorous one, of Gödel's first incompleteness theorem, or the particular version of Gödel's first incompleteness theorem expressed in terms of these F-bar statements. Gödel did not use F-bar statements, used different kinds of statements, but as I said, in terms of the overall moral implications, mathematical implications, logical implications, philosophical implications, this is just as good. And let me restate it. So given what we actually did technically, there are different ways you can package that statement and say it. So in summary, if pi is any formal proof system that is rich enough and no false statement, including F-bar statements, can be derived in pi, then there are true statements that can be stated in pi but not derived in pi. I keep putting this that can be stated just to avoid the completely degenerate case that there's some true statement about something that can't even be expressed or stated because the alphabet we're using is too limited or whatever. No, we have a proof system pi which it's rich enough, therefore it can express, it can state any F-bar statement, but it cannot derive any, cannot derive all true F-bar statements. Okay, so pi is incomplete. So that's what we say. So pi is incomplete. And again, there are different ways you can package what we've done. You could turn it around and say, if you have a rich enough formal proof system that is complete, that is, it can prove, it can derive any true F-bar statement, then it will also have to be true that that formal proof system can derive a false F-bar statement. And that's, if that happens, that's called inconsistency. Okay, that if a formal proof system can prove a statement, can derive a statement S, and can also derive a statement not S, then that formal proof system is called inconsistent. And so we could have given this exposition in terms of that language as well. But I don't need to go there. All right, so I have given here a completely rigorous proof of this version of Gödel's first incompleteness theorem. Later in the course, we will do a rigorous proof of Gödel's second incompleteness theorem, which roughly says that any rich enough formal proof system that is consistent, okay, in any such rich enough formal proof system that is consistent, you cannot prove its consistency in pi. You have to go outside of pi to be able to prove, to establish the consistency of pi. Pi is consistent, but you cannot establish that, you cannot derive that just inside the proof system pi. You have to go outside of it. And one thing I just want to state, Gödel's incompleteness theorem, even the first version of it, the second one is a little bit more philosophical and mystical sounding, but even the first version of it that we did rigorously has been misunderstood many times as something like, in any formal proof system that only proves true statements, there must be some true statements that are not provable. We didn't do that. We did, in any rich enough formal proof system that only derives true statements, there are some true statements that are not derivable. Okay, and this rich enough, in the way we interpreted it, was the ability of that proof system to state F-bar statements, to express F-bar statements. Gödel actually, his first theorem, not the first incompleteness theorem, but his first famous theorem is something called Gödel's completeness theorem, not incompleteness theorem, in which he looked at a formal proof system which was not rich enough, which was much simpler. It only talked about simpler things than all possible statements about integers. And there he proved, in fact, that formal proof system, in that formal proof system, you can establish, it can be that formal proof system is consistent and complete. That is, only proves true statements in that formal proof system, of the statements that can be stated in that formal proof system, and it can never prove false statements in there. So if you make the formal proof system simple enough or poor enough, the converse of rich enough, then in fact you can have both consistency and completeness. So when sort of philosophically or kind of hand-waving, people say there's no, that Gödel proved that no formal system can ever be both complete and consistent. That's not true. But when you get to ones that are rich enough, when you get to ones that are complex enough that allow you to make more interesting statements, for example, about F-bar statements, for example, the way we did it, then Gödel's first incompleteness theorem applies. All right, I'm done. Thank you.